Alright guys, welcome to your video lecture on the law of superposition. Very excited to start this with you. So we've talked, and we did this a little bit out of order, I apologize, it's just what worked best for our virtual schedule, but we should have learned about this before we talked about absolute dating, but that's okay, we're just doing it a little bit differently. So we learned yesterday in our lecture that absolute dating tells us the exact age of the rock, and we talked a little bit about, when we discussed fossils, this relative dating that we'll discuss today, but we're going to go a little bit more into depth with it. So just for a little bell ringer exercise, I want to show you guys a couple pictures of some fossils. So what kind of fossil do you think this is? And you don't need to write this down necessarily if you're virtual with us, but just please listen. This is actually what we call a carbon film. Remember, it is when two rocks smash an organism in between them, and all that's left is the carbon imprint of the organism. In this case, it was a bumblebee. Identified this type of fossil. This is actually an original remain in a petrified fossil. So this man, we call him the Tulin man, was discovered in a bog in Denmark in 1950. It was so well preserved that the two brothers who found him thought he was a recent murder victim. Based on carbon testing, or absolute dating, he lived during the Iron Age and died around 300 to 400 BC, aged 30 to 40 years old. After being hanged, he was laid in a peat bog and a sheepskin cap, a belt, and a noose tied around his neck from the original hanging. So instead of decomposing, because of the peat and the way it works, his body was preserved and able to be mineralized. So his body did not decompose. So in this, I apologize, this is a little bit graphic because these are actual human remains, but it just shows the power of fossils. This man was alive in the BC era, so at least 2,000 years ago, even more possibly, but he was preserved like he just died not too long ago. Peat is kind of like a swampy area. They're typical in areas in England. We might have a couple examples of them here, but they are very oxygen low environment, so that's why this man was able to not decompose. And I'm going to show you a picture of his face real quick up close. This is what his face looks like. So he is so well preserved that you can see the wrinkles in his skin. Remember how we talked about that that the skin and the soft organs are typically the first ones to decompose. So he was preserved so well that those soft tissues didn't decompose. So that was an awesome fossil evidence. What type of fossil is this? This is what we call an amber fossil. Pretty cool. This insect was trapped in a piece of sap, which hardened and became fossilized over time. And then what type of organism, or what type of fossil is this? We know that this is a mold, and this is a cast. Again, mold is the whole, and this organism is actually one of our index fossils, the trilobite, meaning that the rock was formed probably around the Paleozoic era when these organisms were prevalent. Alright, getting into our evolution of landforms and relative dating. So you're going to need out your copy of the notes. If you are in person, you are welcome to take your notes on the physical copies I gave you. If you tuned in online, you're welcome to still do those electronic copies. So who's older? Can you tell relatively who is older? Generally, based on looks, we can tell who is older and who is younger. This baby looks a lot younger than this gentleman on the right-hand side. Some ways we can tell that just because of graying hair, wrinkles, size. Intelligence might be a sign of who is older, wisdom. We can do the same things with rocks. So relative data, what is it? Or relative dating, it helps us, again, remember it was one of those things that helped us construct the geologic timescale. Relative dating is the various relative dating methods that tell you whether an organism or a fossil or layer is younger or older as compared to the surrounding rocks. This type of dating does not give exact age. Remember, just like we said with our fossil lesson, that when we are relatively dating something, we're not giving the exact age of it. It would be like if I was telling you you were school age students, or children, instead of giving your exact age at the number, maybe even month or day that you have spent on this earth. So the absolute dating, like we learned yesterday with our half-lives and our radioactive material, is an exact way to test the dates of rocks. I can tell you exactly how old it is. What we're learning about today only gives you a general idea based on other data that we have found. Relative age. So the relative age of a rock is the age compared to the other rocks. Science determining the approximate order of past events. So we learned the law of superposition a little bit on our fossil lecture. We learned that the bottom layer in a stack of sedimentary rocks is going to be the oldest. So we know that this sandstone is older than all of those above it. And this limestone is older. Layer D is older than layer E. If we were looking at an actual mountain, which you can do, or even the Grand Canyons, you should be able to infer that the older layers, like right here, or the bottom layers, are older than those that are sitting on top. So this layer is older than this layer, and this layer, and this layer. This is what we call the law of superposition. We're going to go into that a little bit more in depth later in the lecture. But again, this is comparative, so we're comparing one rock's age to the other rock's age. It's still not giving me an exact detail or an exact age. We talked a little bit about this uniformitarianism in our lecture yesterday. Again, this is the law that says that we assume that the same natural laws and processes that operate in the universe now have always operated in the universe in the past. So what is happening, in short, what is happening in the past is happening, or what happened in the past is happening in the present and will happen in the future. This theory was developed by Scotsman James Hutton, and he published this theory in 1760. So again, this is the idea that the processes like gravity that I see around me today happened in the past. So when the dinosaurs lived, there was still gravity, and they'll happen in the future. So when we have flying cars, there will still be gravity. Okay? It's an assumption. We're not exactly sure if it's true, but it's what we assume. So we've got some clues that support our relative data and our findings. So basically, these are what we use to support the idea that relative dating is a good and scientific way to date our rocks. We use fossils to help us. We use the law of superposition. We're going to talk about unconformities, and we'll also talk about ice cores and how they further our knowledge about the age of a rock. Let's start with fossils, shall we? We've spent a whole lecture on fossils, so much of this should be review for you. What is a fossil, and what does a fossil tell us? What's our goal? So the fossils, again, they're preserved remains of a once living organism, very similar, if not word for word, what we learned about the other day. Fossils give us clues about organisms that lived long ago. They help to show that evolution has occurred. Again, this is going to be lots of review. So through fossils, we can find organisms with similar characteristics to what are living today. We can find links in between common ancestors long ago to what we see today. They can also show adaptations that organisms have evolved over time. So one of those is limbs, 4 limbs. Another of those is changing from aquatic organisms or ones that live in the sea to ones that live on land. We can find fossils of organisms, and we have, that kind of show that middleman species between what we have today and what our common ancestor was. So fossils are really important in linking the past to the present. And they also provide evidence about how Earth's surface has changed over time. Remember, we talked about if we find certain organisms in our rocks, we can predict about the climate that was happening when that rock was formed. For example, if I find a seashell on top of a mountain, I can assume that that mountain at one time was covered by water, meaning that the climate of the Earth, or the surface of the Earth, was once underwater at that level. So we can see how the oceans and the land masses have changed over time. And lastly, fossils help scientists understand what past environments may have been like. So again, nobody lived 4.6 billion years ago. We just didn't. Nobody lived like 300 million years ago. We didn't. We hadn't evolved yet. So scientists, because they don't have any firsthand data passed on from other scientists, they need to rely on fossils and other evidence to get an idea of what the Earth was like in its geological past. Let's talk about how a fossil forms real quick. So we went over this a little bit yesterday, but we'll talk about it one more time. So the very first step is that sediments happen. So an animal is buried by sediments such as volcanic ash or silt shortly after death. That happens. And oftentimes those sediments will delay decay of that organism, meaning that parts of it will still be preserved. Hopefully all of it. We want the skin and everything, but most of the time it's just the bones. And then more sediment layers will accumulate above the animal and slowly replace the calcium phosphate in the bones. So our bones will become rock, basically. So when you're finding fossilized bones, they're actually rocks. And after the layers formed, we will get movement. So the movement of the tectonic plates, or giant rock slabs that make up the Earth's surface, will lift up the sediment and push the fossil closer to the Earth. So it's possible, if the tectonic plates hadn't moved, that we wouldn't see any of these fossils because they would be buried deep down below the surface. But because we have disturbances in our rock layers, which we talked about yesterday, or Monday, Tuesday, these fossils are coming to the surface so that we can not so that we can investigate them, they're naturally coming to the surface, but because they're at the surface, we can investigate them. And then lastly, erosion will wear away the remaining rock layers, exposing the preserved remains, where somebody may stumble upon them. Now, we do know that paleontologists and archaeologists dig for these remains to try and find them, but sometimes they just come up naturally. We have, again, 5, debatably 4, main types of fossils. Petrified fossils, like our man at the very beginning or our dinosaur bones. Molds and casts. Remember, molds are the holes, cast is what fills it. Carbon films, trace fossils, and preserved remains. And we'll go through those quickly again because we've already studied them. Here's our petrified fossils. So petrified fossils form when minerals replace all or part of an organism. Water seeps through the layers of sediments to reach the dead organism. When the water evaporates, only the hardened minerals are left behind. Okay, so this might be how our friend T-Rex here actually came about. We've seen that guy actually in Chicago. Okay, so this is where minerals will replace all or part of an organism. So minerals replace the bone cells. Molds and casts. Again, a mold forms when a hard part of an organism are buried in sediments. The hard part will completely dissolve over time, leaving behind a hollow or hole area with the organism's shape. See the mold? And later, a cast might form as the result of a mold, so more sediments are going to fill this, and then they're going to cement themselves, and they'll form a cast, or a rock version of that organism. Mold is the hole. Please remember that. Write that down somewhere. Star that. I don't know. Write it on your bathroom mirror with an expo marker. Write it down on a sticky note and stick it up beside your bed at night so you remember that. Mold is the hole. And then when the water, excuse me, I didn't know there was more. The water with dissolved minerals and sediments fills the mold's empty spaces, and a cast is the opposite of a mold. Fantastic. Here's how it happens. So our mold forms and our organism will eventually decay, leaving that mold hole. Again, mold is the hole. And then sediments will eventually fill up the mold. Sediments will go over the hole and fill it up, and then we'll get many more layers of sediments until it completely fills it. Then if we were to break the two apart, we would get a cast. That is where the sediments have filled up that mold. All right, guys, check out the next lecture for the remainder of your notes.